In the textbook, we looked at the stability of linear maps described by a matrix, and that matrix had two distinct eigenvalues. And in that case, the conclusion was that you should look at the magnitude of these eigenvalues, and if they were all smaller than 1, then you had a stable fixed point. Now, what happens in case the eigenvalues are not distinct but are the same? In that case, you cannot use that same proof because the canonical form of the matrix is different. If you go back to your kindergarten linear algebra courses, then you might remember that for that particular case, you can write down the matrix A as a matrix Q times a almost diagonal matrix, but with a 1 here in the top right, times the inverse of Q. So that's a different canonical form. If you had two different eigenvalues, then this would be lambda 1 and lambda 2, and you would have a 0 up there. Now, the aim of this exercise is to see what happens if you take this matrix and you raise it to an arbitrary power of m, and then draw some conclusions related to the stability of the linear map from that. So pause the video and calculate arbitrary powers of this particular matrix here. Let's first start with the matrix A squared. So A squared is going to be given by Q times that matrix times Q minus 1. So that's A. And then we write down A once more. And then the good news is that Q and its inverse cancel here. We're also going to introduce a shortcut. So if we have this sign here, it basically means sort of like matrix proportionality if you want. So that's just a shortcut for adding Q to the left and Q minus 1 to the right. So we're going to say that our matrix A squared is proportional, if you want, to lambda 1, 0, lambda times lambda 1, 0, lambda. Okay, so that way we don't have to deal with all of these Q's. We can multiply these two matrices. It's a piece of cake, going to give us lambda squared, and then we have lambda plus lambda, so that's going to give us 2 lambda. For the lower left rather, it's 0, and here we have another lambda squared. So we can factor out lambda to give us lambda 2, 0, lambda. That's A squared. That was fun. Now let's do A cubed. A cubed is obviously A squared times A. So that's lambda, lambda 2, 0, lambda, and then times A. That was lambda 1, 0, lambda. Now if we calculate this thing, that gives us lambda times, and then we have lambda squared here. And then we have lambda plus 2 lambda. 1 plus 2 is 3, if I'm not mistaken. And then we have lambda squared here. And that's going to give us, again, factoring out the lambda squared, lambda 3, 0, lambda. Now in this case, the pattern should become clear. If not, then just calculate a to the power of 4. But in general, a to the power of n is going to be proportional to lambda to the power of n minus 1. So indeed, if we had a 3 here, we had a 2 there. If we had a 2 here, we had a power 1 there. So we factor out lambda to the power of n minus 1. And then the matrix itself is lambda n 0 lambda. Okay. Now that will just very easily allow us to calculate what happens to a certain orbit. So a to the power of n on x, y. The question is, what will happen to that orbit? Will it move towards 0? Will it blow up? Now, in the limit of n going towards infinity, you might be concerned for this n here, because this will go towards infinity. But it will go towards infinity in a linear way. So everything that happens inside this matrix here is going to be dwarfed by this guy over here, which is in essence an exponential factor. So everything that happens here is dominant, basically. So here you can also see that as soon as lambda, the eigenvalue, is smaller than 1 in magnitude, then this whole thing will collapse back to 0. So this really shows that in that case, the origin is a stable fixed point. So the same conclusion that holds for matrices where the eigenvalues are different also holds for matrices where the eigenvalues are the same. But the way to prove it is a bit different because the canonical form is a bit different.